2 minutes more. If you have anything to ask or say, please do. Please do. But again, as I have said a number of times, you should not worry too much about what goes down and what remains overflowing, okay. Because time is short and good things need time. So, okay, don't. But at least we have started to communicate some ideas, and you are much, not only younger, but also much smarter than I am, so you will take them to profit more than I have. If you will like to do so, because there are many things, many other things that you can consider. And for the exam, I understand it is going to be a multiple choice. Maybe I will prepare tomorrow, but with four or five questions, I will see about definitions of the main few objects. Okay, so that shouldn't bother you too much. Like how a Lyapunov exponent is defined, an invariant probability, just simple things like this. Then today you start, I guess, more with applications with Professor Fataf. So. And maybe it's time to start. Okay, so today we go on with the theory of probabilities for dynamical systems, but then also for what are called stochastic systems, okay? Anyways, first, let me see, this we have already covered. Yeah, okay, so it is time to say something about stochastics. Maybe we can eliminate this whistle here, because, well, it stopped. Okay, so the first thing we need to know is the notion of a random variable. Okay, let me take my iPad, because so I don't tell you something wrong. Because I made notes for myself this morning that you find also in the Dropbox. Huh? This? Okay. Okay. So the first thing we need is to define a random variable. A random variable is basically everything. Can be everything. Okay? A random variable is a measurable function, but we don't do anything without measurable functions, okay? What is a measurable function? Actually, I didn't tell you. A function is measurable if it maps measurable sets in measurable sets. What are the measurable sets? The measurable sets are those that belong to the sigma algebra. Okay, so because they are the ones that you have decided they should be measured. Okay, and then a function goes from a certain measurable space, that usually we called it M, to another measurable space, which in these notes is called S. Now, there is a sigma algebra here and there is a sigma algebra here, and the measurable function takes the measurable sets here to the measurable sets here. That's nothing more than that. Okay, for instance, continuous functions are measurable functions. Now, what is a random variable? A random variable is a map between two measurable spaces. In fact, we have to say a little more. We have to say that in the space from which you start, you have a probability. So you need to have a triple, which is M, sigma, the sigma algebra, and P, a probability. Usually we called it mu, but here they call it P. It's the same thing. Okay? Then any function, okay, that goes from M to S that is measurable, and so in S we have to have another sigma algebra, call it sigma. Okay? Any function of that kind is called a random variable. Why do you call it a random variable if it is a function? Because you assume that this function is not known. Okay? It's not known. It is known only with some probability. That's why we need a P. So, for instance, say the result of tossing a coin is a random variable, because you toss the coin and you know that you will have head or tail, but you don't know which. Okay? You only have a probability. So this is a random variable. Now, what is a stochastic process? So this is random variable. A stochastic process is a collection of random variables that are indexed by a certain parameter t. Okay? So a stochastic process becomes a collection of variables xt such that t belongs to some set. And we call it t because usually what we mean is something that changes in time. So t stands for time. But it is not necessary, okay? It could be a place somewhere. But the standard thing is to have something that is ordered. So if t is a number, is a real number, then it is ordered. Okay? The smaller number, the numbers to the left come before the numbers to the right, and there is an ordering on the real line. You have an ordering on the integers. So real and integers are usually the most simple sets of parameters, but they could be an interval. You know, in relativity, certain phenomena, I mean, random phenomena in relativity are quite a complex business. And to define them, in fact, one of the complexity comes from the fact that you need this to be, for instance, a 7-dimensional space. Not good. Not good, because that is not ordered. Okay? Like, it's enough you have a 2-dimensional space and there is no ordering. Okay? Does this point come before or after this point? There is no ordering there. Okay? In some sense, there is what is called the partial ordering, but here that doesn't even work. So in any case, for us, and not only for us, but very most commonly, a stochastic process is a collection of these functions. What do we do with this parameter? Well, for instance, we spoke about tossing a coin. Then you can have tossing a coin at time 0, tossing a coin at time 1, tossing a coin at time 2, and so on. Now, the sequence of this tossing becomes a stochastic process. Okay? The temperature that we mentioned various times is a stochastic process because maybe we can reduce this a little because it whistles, it goes beep. The temperature, the moment that you measure it is not random. Because you measure it, it has a value. Like when you have tossed your coin, and then you see it is either head, okay. It is either head or tail. It cannot be both. Or it cannot be head with some probability and tail with another probability. Okay? If it is head, it's head. So it is not random anymore. The same way, temperature now, if I take a thermometer and I measure it, is what it is. Maybe it is known with a finite precision because every measurement tool only gets things with a finite precision. But it is known, so it's not random anymore. But if I want to say what is temperature tomorrow, and then the day after tomorrow, and the day after the day after tomorrow, okay, these constitute a stochastic process. In this sense, temperature becomes a stochastic process. Okay? It is a function. Now, we may know the rule of evolution. In dynamical systems, we know how evolution takes place. Okay? X dot, we said, equals to some g of x. This is a special fortunate case. Although it is very complex. Stochastic processes are easier in general. You can get many more results for stochastic processes thanks to the fact that you already have a probability. While here, probability has to be built. You remember? Huh? I gave you the recipes to build what probability will be at a later time, and so on. Okay? So this is really very brief about random variable and stochastic processes. Now, what do we do with them? Well, they also correspond to an evolution. Huh? If we say that this is time, they also correspond to an evolution. This evolution includes also this. Okay? Only that here you have to do more work. Here part of the work is already done. But there are many cases, as I said at the very beginning of our classes, that we cannot write like this. We cannot write like that because maybe a formula like that doesn't exist. Or simply because maybe we don't know. We don't know that there is a G. If we have to place a camera on a comet, we know G. It has got to do with the law of gravitation. But if we have to speak about investing money on the stock market, well, then forget about knowing this. Okay? There is no chance. So the only possibility, if it exists, is that of a stochastic process. And in fact, stochastic processes have been largely developed in the field of economy and finance. Nobel Prizes have been given to mathematicians and economists that were like mathematicians, an Italian, for instance, or the very famous mathematician from Princeton, who was also a character of a movie, The Beautiful Mind. Okay? mathematician, he got the Nobel Prize for economy. Okay. Well, because he knew how to deal with mathematical models. And the Italian now, it escapes me, he was in Chicago. Well, anyway, he got it precisely for stochastic processes. Now, how can we go about the evolution of a probability in a situation that is so wide and allows everything? Well, something can be done. Something can be done, so let's take a look at this something that can be done. Suppose that our probability is absolutely continuous with respect to the volume, the Lebesgue measure on this space M, and so it has a density. Suppose the probability has got a density that I call W in these notes because it is the notation used in various books on stochastic processes. And if you are interested, two good ones are one by Gardiner, edited by Springer. Now I don't remember exactly the title, but you search for Gardiner stochastic, you find the book. It's very easy. And the other one is Risken, which focuses more on one way of solving the evolution of a stochastic, the evolution of a probability density under a stochastic process, and which is the Fokker-Planck equation. And I'm going to write the Fokker-Planck equation today, I hope. And in the book, there is the title of the book contains Fokker-Planck. Anyway, these are two. These two books can be recommended. Okay, so we have our probability. We want to see it evolve. So our probability will be defined on Z, where Z is in our space, would be our M. Okay, and we want to know what it will be at a later time. Okay, T is the time where we are, and we want to see what this becomes after a certain interval tau. Okay? How can we get this? Well, we can use some definition, which are tautological. Okay? They don't add any information because they just repeat what we know. But it's always a good idea to start from what we know. You see the eraser somewhere? Huh? Ah, up there, yes, thank you. So we will say this, which becomes a definition of a certain quantity. We will say that this is equal to integral over all possible values Z of what is called a transition probability that takes you from time from Z at time t, that takes you to Z at time t plus tau, because this is what you want to get, starting from somewhere else at t. Z dash at t. Okay, times what the probability density was earlier on in Z dash. And then you integrate over all possible starting points. Okay? Now, this is one reflection of what is also called the formula of total probabilities. It is specified in this. What is the probability of going, maybe I do it here. Say you want to be here at time t plus tau. In the stochastic process, maybe you want to have head. Okay, you want to be there, so this is Z, you want to be there at t plus tau. What is the probability of being in Z at t plus tau? Is the sum over all probabilities of having been in other places at time t. This is another Z prime at time t. This is another Z prime at time t. Okay? So you had the probability of being here, being here, or being here. That is given by our probability density times dz at time t. And then you will have a certain probability of going there. And this is our p. Of course, you may have a probability of going somewhere else. Okay? So the meaning of this formula is to sum up all the contributions that go there. This formula does what we have called so far the preimage, in some sense. Okay? Not in some sense, it's like the preimage. This is the preimage. Only that it is not on the sets, it is already on the probability. Okay? Yes?
Tau should also be in the T?
Sorry, what about
Tau.
tau? Yes. No, this is the time lag. How much later you want to go? You are at time t, and then you want to be a later time there. Okay? So tau is another thing that usually you would take larger than 0. It is for a later time. Okay? Yes, please stop me anytime. Okay? Stop me anytime. Now, we call this transition probability. The meaning is obvious because it gives you the probability of going of transiting from here to here. But it's still a probability, so it has to obey the usual properties of a probability, which is probability of z t plus tau given it was z prime at time. Yeah, this is how you read it, okay? With this vertical bar here, you read it as probability of being in z at time t plus tau given that it was in z prime at time t. It is a probability, so it must be bigger or equal than 0. Moreover, if you integrate over all possibilities, you have to get 1. So, what are all the possibilities? Look, it is integral of p z at time t plus tau, given it was z prime at time t, integrated in all possible outcomes. So, at time t plus tau, you will have to be somewhere. If you consider all possible places where you can go, then you certainly go to one of them. So, this has to be equal to 1. If you want to go to a specific place, it will be something smaller than 1. But if you start at time t and in z prime, and you go somewhere, you surely go somewhere. It could be even remaining there. Okay? So, say you started from this point, you integrate over all the other points, which include this, and itself, then that must be 1. Okay? Now, these transition probabilities can be quite ugly and complicated if they correspond to a deterministic dynamics, which is dissipative. I don't remember if I told you, but dissipative means that lambda of x, which was our divergence of the vector field G, is negative. Maybe it fluctuates, but then it must be negative on average. Okay? So, for dissipative systems which contract volumes, you remember that the divergence is the contraction rate, is the variation rate. If it is negative, means volume contract. Then the set where you are going to go is ugly. Okay? Ugly in the sense it can be beautiful. The Mandelbrot set is beautiful, but it's hard to handle. Okay, so the mathematics becomes quite complicated. Okay, we will not treat those cases immediately, although many of them can be treated. This is just to tell you that there are some kind of processes that we exclude. Many of this kind can also be included. Okay? So we will say that our process, the stochastic process that corresponds to this evolution of probabilities, is regular. And what does it mean that it is regular? It means that it has some decent continuity property. So what we say, it is regular if limit for the time lag tau going to 0 of p of z at time t plus tau, given that it was in z prime at time t. So when you approach the initial point, our probability becomes a Dirac delta function, okay? Which is not a function, you know. It is called function loosely. It is an operator. It is an operator that you can use inside an integral, and then if you multiply by the integration element, it becomes a measure. Okay? This is to say that if the lag time goes down to 0, you have probability 1 of sitting where you started, and probability 0 of being anywhere else. So it's not too bad to require. Okay? In deterministic systems, this will be good for most of the times. Okay? If you have a smooth vector field, then that is going to be true. If the vector field is not smooth, then that is not going to be true in general, because if the field is something like that, okay, and you sit here arbitrarily close to this point of discontinuity, and here, and say you call this z prime, sorry, you call this z, no, this is z prime, okay? And by taking time to 0, you go either like this or either like that. You see that it is not going to be the same, okay? If z prime was here, then when you take the limit, taking the limit doesn't mean evaluating the function on the spot. It means approaching. Well, if you approach this way, you go to a different point. So the field, the vector field, should be decent. Otherwise, this hypothesis doesn't. Unfortunately, discontinuous vector fields are everywhere. Okay? So this gives you an idea of what we are eliminating. I drew for you yesterday one of these discontinuous vector fields, but this is easy to handle because the discontinuities are placed in a countable number of spots, and they can be clearly identified. But if you have a point particle that moves within flat walls, it bounces elastically, it draws a trajectory like this. Well, these are discontinuous points for the vector field because the trajectory in positions space is continuous, but the velocities are discontinuous. And you remember that in our points gamma, okay, we included both positions and momenta, which is also velocities. Okay? So this picture would have a difficulty to be applied here, except that we can identify these discontinuity points, and what happens at them is also clearly identified, so it is a situation we can handle. But a situation that the people learned to handle quite recently. Not for you, because you are all very young. Okay, but it was in the 70s of last century, so it makes 70 years ago? No, 50 years ago. 50 years ago. Oh, it's a sizable time, but it's not much for me. Okay, so we will have this kind of processes, regular ones. Okay? Now, because you have a probability, probably you know, but I didn't tell you, with a probability you can compute not only averages, expected values, but you can compute the properties that are called moments. Moments are important, are very important to characterize the probability. So I call Mn of a certain variable x, the integral over the whole space, so I don't write here because I didn't specify the space, of x to the n, we used to call it mu, but now to use the stochastic notation, I call it p. Okay, it is the p that I have here. So this is an average. It is an expected value. Okay, it is the expected value of x raised to the n power. Okay? So we have a probability. Although it is a special kind, it is a transition probability, but it will have its own moments. Okay, these are called moments. How many of you have already heard about this notion? You know. Anyways, that is the definition. Okay? Nothing mysterious, although it has a lot of consequence. So this is moment, nth moment. So also the transition probability has got moments. And let's call it Mn. Okay, Mn z prime t and tau. Okay, we take it function of the three variables: the starting point, the starting time, and the lag time. Okay, that is equal to integral. Now, in my notes, I decided to consider a one-dimensional process. Okay, so this x takes value in the real line. So here I write an integral from minus infinity to infinity, but in my notes. But you don't need to. Okay, but let's make it simple, like in my notes. So let's say that xt goes from my space M to the real numbers. Okay? Then here I can integrate over all numbers from minus infinity to infinity of this quantity, z minus z prime, raised to the nth power, p of z at time t plus tau, given that it was in z prime at time t, dz. Okay? So this is the nth moment with respect to z prime of the probability P, of the transition probability P. I have integrated over Z, so it remains dependent on the other parameters. Now, a function that is exceedingly useful in dealing with probabilities is what is called characteristic function. Now you remember that I called characteristic function the function of a set that is 1 when you lie in the set, is 0 when you are outside the set. I told you this is the language used by analysts. Probabilists call it indicator function. Well, because for them the characteristic function is what I'm going to write now. Okay? It is something totally different. So let us introduce the characteristic function. C, of course, for characteristic, is a function of U. You will recognize what it is in a moment. Z prime, T and tau. And is defined like this. It is a Fourier transform. Okay? It is the integral from minus infinity to infinity of e to the I u z minus z prime probability of being in z at time t plus tau, given that you were in z prime at time t dz. Okay? So it is a Fourier transform with respect to the variable z that then in its Fourier space it gets replaced by the variable u. Now this function, it can be proven. It's not even particularly difficult. You have to expand the exponential. You know that the expansion of exponential exists, so you are safe. You expand the exponential as a Taylor series, you get powers. And the powers will be these ones, plus coefficients. So you see that the characteristic function is related to the moments through an expansion. And in fact, this will be equal to 1, because the integral of 1 with a probability is 1. It is its definition here. If I multiply by 1, nothing changes and I get 1. So first term is 1, and then there is a sum that goes from 1 to infinity of I u to the n divided by n factorial times the moments mn of z prime t and tau. Okay? Now look, you recognize the moment. Okay? It is what is left. Once you have taken away IU to the n. Now, what have we done so far? Basically nothing. Okay? We have only introduced objects that depend on an unknown object, and therefore they themselves are unknown. But we have prepared the stage for more that we will see in a minute. But you should excuse me a second. I come back soon. Okay? Just give me 1 minute. This maybe doesn't come with me. So yes, we have done nothing, but we set the stage. Let me recap. We have a process. It is called stochastic because it is known only through probabilities of what will happen. Unlike the function y equals x squared, that is not known with probability. Ooh, thank you. Okay, if I write y equals x squared, that is known with certainty. You give me 1 and you get 1. You give me 5 and you get 25. This can nevertheless be included within a stochastic process where the probability is 1 for the right values, those that have this form, and is 0 for all the others. So the framework is very wide. But in general, it happens that you don't know what it is. So so the probability is something more complex. And this probability can change in time. And if we are lucky, the probability has got a density. And now we are in the case in which the probability has got a density. Now, the reasoning goes this way. There is a density that changes in time. We don't know so far how it changes, but if it changes, there will be some transition probability that makes it change. So I don't know this, but I know that it exists. I don't know this, but I know that it exists. So this equality here becomes the definition of the transition probability. Okay? Now you tell me you know nothing about it. True, because I know nothing about this and I know nothing about that. But because I know that this exists and this exists, how do I know? I have assumed it. I'm in the framework in which it exists. because I know that they exist, then this must exist. So this is the definition of P. Once I have defined the P, because it is a probability, it has to have these two properties. It cannot be negative, and its integral must give you 1. Well then, somehow, okay, it will have moments. And this is an extra property that we have required to make the calculations that now you will see I'm going to do. Okay? So we have done nothing. We have gone from unknown to unknown. But let's see if we can go beyond. And we can do it after we have introduced the characteristic function. Okay? After we have introduced the characteristic function, we can write the following. We can say that because this is a Fourier transform, if we are in a world where things are regular, and all these also regularity properties are satisfied, then like P has a Fourier transform, the characteristic function has its own Fourier transform, which is the anti-transform that takes you back. Okay? So we can say that P of Z at time t plus tau, given that it was Z prime at time t, is equal to, now this is the anti-Fourier transform in one dimension, 1 over 2 pi integral from minus infinity to infinity of e to minus iu. You see the difference between transform and anti-transform basically is that here you have a plus and here you have a minus. This factor 1 over 2 pi that is missing here is conventional. So mathematicians prefer to see things in a symmetric fashion, and they would define the transform as 1 over root of 2 pi integral from minus infinity to infinity e to the iu whatever, and then the anti-transform as 1 over root of 2 pi integral from minus infinity to infinity of e to minus iu whatever. So this becomes symmetric. Okay? And transform and anti-transform constitute together an involution, something that you apply twice and you get back where you started. It's unitary transformation, written in this way. Physicists and engineers in applications, for reasons related to their work, they prefer this other convention, that the transform has no division by 2 pi, and the anti-transform has division by 2 pi. So the root 2 pi gets cumulated in here. It is the same thing. It's only convention. Okay? Of course, quantitatively you get the difference. But the calculations go along exactly the same. So now, this, okay, the anti-transform of the C takes me back to that. Okay? So it is 1 over 2 pi e to minus u z minus z prime of the function C, the characteristic function that depends on u. What is the order? U, z prime, t, and tau, which I have just defined. And this will be integrated with respect to the Fourier variable, which is u. Okay? This removes u and gives you back the z. But for the characteristic function, we have written this expansion. So this can also be written as, let's see if I can fit it, maybe better go below, 1 over 2 pi integral from minus infinity to infinity of e to minus I u z minus z prime of the expansion, which is 1 plus some in n from 1 to infinity of IU raised to the n power divided by n factorial times the moments mn of z prime t and tau, all this within brackets integrated in du. Okay? All these things are unknown so far, but they are what they are. Okay? All these things, given our definitions, are perfectly legitimate. But now look carefully. Look carefully what we get. We are going to get an equation for the evolution of the probability density. Now, the probability density is unknown, but I will have a rule to compute it if you give me the initial condition. Okay? So, let me see if I have time to write this. Yeah, because we have little less than 15 minutes. So, I should be able to do it. So, what is the product that we have in this integral? I have a question? Please, please. What?
Because there is t.
I know, but we started a bit late. Do you want to go to tea? I finish on Friday then. I stop here and I finish on Friday. Okay, let's go to tea. Let's go to tea. I stop. Yeah, because we started late, but it's not their fault. Then the tea gets cold. Okay, I see you on Friday. Have a good day. Yes?
We call it moment, like these.
Moment. And that honestly, I don't know.
Somewhere I read there's some concept related to moment of inertia, and they are saying that we are trying to see how your data is deviating from the mean or something. Is it true or
No. Okay.
Understand. Hello?
Yes.
Yes.
You can make it little more above also, that mic.
Again?
Yes, yes. That mic you can keep
Higher.
higher.
Here? Okay. Okay.
This board and this one, right?
Yeah, I think maybe here, this one, because easy for me to walk. Ah, is it okay? Because I'm afraid
You can come up to this.
Yes.
You can keep little bit towards you. You can come up to this.
Yeah, sure.
So on behalf of the organizing committee of this GIAN program on Dynamical System and Trial Theory, IoT and Cryptography applications, you all would have attended the past 5 lectures by Professor Lam, University, National Defense University of Malaysia, will handle the classes. For the next 4 lecture hours and 2 tutorial hours, we will handle by Dr. Dynamical. His expertise is IoT and cryptography applications. She has vast knowledge in modeling, signal processing, and secure image communication. So these are nowadays very important because there are a lot of hacking and many things and digital frauds and many things are happening. So how one can predict, not predict, prevent themselves when sharing very important information and other things. Without any further delay, I welcome Dr. Noor Aisa Bhatta to this GIAN course.
Yeah, thank
And
you.
the podium is yours.
Yeah, thank you. Thank you. Thank you, Professor Silverash. Okay, so yeah, as mentioned, you can call me Aisha. It's actually Fataf is actually my father's name. So in Malaysia, we use our father's name as the initial. So my exact name is Aisha. Okay. Okay. So I'm writing here is lecture 1 because it's a lecture 1 for me. So basically, it's a lecture 6 for you guys. Okay. And my lecture today for this 1 hour is a basic understanding of chaos. Professor Lamberto already mentioned a lot of times about chaos. So today I'm going to briefly explain what is chaos for your understanding. Okay, and just want to mention I'm wearing the same scarf here. I didn't plan it. Today when I will check my slides. Oh, I'm wearing the same scarf with the pictures given. Okay, so yeah, that one is different. That one is green color actually. I suppose I have to give the same, right? Okay, so before we start, I would like to introduce my university. I love to introduce my university because in Malaysia we are a unique university. So in Malay we call it as University Pertahanan Nasional Malaysia, and in English we call it National Defence University of Malaysia. So there is a defence in there, meaning that actually we are teaching a soldier, a future soldier. We are teaching future soldier. We call it cadet. So you can see I have few students in cadet and now already become officers. In fact, might be a major now and higher salary than me because they got so many allowance there. So yeah, university. I mean UPNM. We call it as UPNM. In fact, giving a salary to the students, to the cadets, to learn. In fact, the fee is also free for them. They are giving, not allowance, sorry. They are giving a salary, okay? A salary, and also they included the allowance also for the student. So when we are talking, I mean, our staff talking about the bonus, they also will talk about the bonus because they are given as same as the government officer. Even they are doing students, in particular in university. So that is good for them. And but then I think maybe the best part for that is they have to undergo a physical training marching, they have to tolerate with so many peoples in, you know how military act is, so that is what they have to pay for it. So basically during morning 8 to 4, they will go for the classes, and after that they will go for the training. Okay, the training is supposed to be up to 10, because after 10 they will set light off. But knowing military, there will be like no turning off lights. But yeah, we actually as faculty members didn't involve with that. So maybe sometimes we have to hear, ma'am, I cannot do this assignment. My officer asked this and this. So I sleep at 5. So I have no time to do my assignments. That is always the, you know, the reason. I mean, the excuses they are giving to us. But then, yeah, as a staff, I mean, as a lecturer, we have to be more strict, and if not, they will not listen to us. If you are, oh, it's okay, you take the time. No, we cannot answer that way. So whenever we set the due date, so they have to do the due date. So basically, what they will do is like copy paste. So that is actually the best of military cadets. But then they are actually very clever. If we can compare with the civilian, actually we also have a civilian nowadays. But even they are always copy paste the assignment whatsoever. But then their exam, actually they are perform well. So that is the best part of the cadets. In fact, nowadays our government's changing a bit. So the student more likely to have, we more likely to have the civilian rather than the cadets now. Maybe because we produces graduates cadet every year, so the military officers is already increasing, so the needed is less now. So that's why we only maybe about 30% of the students is the cadet, and another 70 is the civilian. So if you can see in this figure, a lot of cadets. This is my previous long before, maybe 10 years before. So currently, I would have about 5 cadets out of 30 students. So in my class currently this semester. So it reduces. So, and I'm happy because I don't get so much damn reason and excuses from them. Sometimes they are not coming also. Ma'am, my officer is calling. So many excuses you can hear from the cadets. And cadets love to give the excuse. Okay, but then yeah, they are clever. Okay, so that's all from my university, UPNM. I just want to make you guys remember me, so you can remember my university. Okay, so this is the outlines that we go. It just actually for today, for this 1 hour lecture is very simple. Just the introduction of chaos theory and the nonlinear system. So we go for introduction to chaos theory. So what is this chaos theory is all about? Okay, so it's actually chaos theory is developed by mathematicians. Which is they observe certain system do not behave as traditionally we expected. Like for example, if we have linear equation, whenever you put it input, you will get the output. So you'll be proportionally behavior between these two. So for this chaos theory is actually they do not behave traditionally as what we expected. So it's actually we get unpredictable. So chaos theory we always comes to unpredictable system where we encounter this system to be unexpected and a very incomplex behavior. And classical tools of calculus actually is not inadequate to understand this system. So this inadequacy comes to the new field of chaos theory. Okay? And actually, chaos theory is a deterministic nature because it's governed by a rules. We are giving them a rules, but then they exhibit random behavior. Okay, they are exhibit random behavior and unpredictable. So meaning that there are fixed equation. There are fixed equation for the system that govern the system. However, they often display as a random and unpredictable. So this randomness where the magic is lies. You know, because you are like to be structured, but then you are not structured at all. Okay, so that what we call magic of chaos theory. Okay, so the core concept of chaos theory, there are 4 that I list here. The first is, as I mentioned, is dynamical system. So when we talk about dynamical system, we should have the equation. So, and the equation for dynamical system, when we talk about chaos, it will be non-linear dynamical equation. And we can have few examples of the system, like pendulum for physical system, biological system. We can talk about population dynamic. So this is the example. Economic system, stock market fluctuation. So there are many more. Actually, there are many more. In fact, nowadays, when we have the COVID-19 and so much of the virus infection, right? So we can model the system, and that system will predict will be in chaos. So means that we cannot predict the behavior, and it will be exponentially growth, as you can see in COVID-19. Okay, and I just mentioned just now non-linear. So the chaos should be non-linear. So the output is actually not proportionally to the input, whereby like we have like as I mentioned just now, is a very simple equation. If you have y equal to 2x, if you put x equal to 1, the y will be directly for the y equal to 2. So it's a direct proportional. So now for the non-linear system, it will be not directly proportional. So means that there will be a loop. Okay, we develop a feedback loop where small changes can be amplified or suppressed. So means that the loop will make the system amplified. It will be maybe a bigger, or it will be suppressed. Okay, so that's why it will make the system complex and unpredictable. And just now also I mentioned deterministic system because it governed by a equation. There is some rules that govern the system. So actually it can be predicted in the short time, but we cannot predict in the long time. Because in practice, the small error will grow exponentially. So we cannot even predict in the long run. Okay, and lastly is randomness. So it is the system is exhibit behavior as a random, but then it's root as the deterministic system. So this all is a core concept of the chaos theory. Okay. So to define chaos theory is actually a branch of mathematics that study complex system, whereby the behavior is highly sensitivity in initial condition. I make it short as an initial condition. So this is what we call it deterministic chaos. Okay, and Okay, so what does we mean by sensitivity to initial condition? So it means that if we put a small difference, or maybe we would say insignificant difference of the initial condition, but then the output will be very different from the initial what we expected. So means that tiny changes in our initial condition will give us a different result of the output. Okay, and then it's also the same as I mentioned. Actually, what made this system fascinating is that they evolve over time. So they evolve over time. They are following the specific rule. There are specific rules that they are following. But then the outcome appeared very random and unpredictable. So even, for example, if you want to check the weather, the temperature is reading like 30, for example, but then then we put it in our system as 30, but then the real temperature is actually 30.1. Okay, so the reading from the temperature is 30, yeah, but then you know the reading of our tools might have some error. So in actual temperature surrounding is actually 30.1. So it's just a difference of 0.1. But then the prediction comes later will be very, very different in these two cases. Even it's just a very slight difference of 0.1. So that is what chaos theory is about. Okay, and I will explain the key characteristic, which is deterministic yet unpredictable. Okay, so it's actually the system governed by a set of rules, but then the outcome is unpredictable over time due to the exponential sensitivity to initial condition. Okay, we can see the example as the double pendulum here. Is it I can run? Okay, I can run again. So double pendulum, you can see the initial is actually almost the same, but then when it comes evolve over time, the result is actually very diverge from each other. So that is what I mentioned, the sensitivity of the initial condition and nonlinearity and complexity. Okay, so this is the source of chaotic behavior. So small changes in the part of the system can have disproportionate effects on the whole system. Okay, so actually mathematically nonlinear can be expressed as like product term, trigo, exponential, a power of variables. So in the system, if you have this term, this nonlinear term, for example, the product rules, the powers variables, exponential, trigo, so this system will make our system chaotic. Okay, so my question to you, have anyone ever observed any system in daily life where a small initial change lead to a big or unexpected outcome? Okay, means that anything that you have observed in your daily life, in where the small changes actually will lead to unexpected outcome. Come again? Compounded iteration. Interest. So as I mentioned just now, you mean is a financial stock market. Yes, that will be correct. So fluctuation in the stock market is also unpredictable. So yet even there is a tiny difference or tiny what we call announcement will be very affected the system. That is very good example. I would share you one. I don't know. It's happened to me every day, because whenever I go to my university, I use a car. So it happened to me whereby a traffic jam. And surprisingly, I encountered a jam, traffic jam. The road is very congested. But then when I go through, nothing there. There is nothing. There is no accident. There is no stopping car. But then, what is a traffic jam towards the end. So it's nothing. But then, traffic jam is occurred. So why do you think that is happening? So I will share you one video. I would say this is interesting to explain why a traffic jam is occurred.
You're cruising down the highway when all of a sudden endless rows of brake lights appear ahead. There's no accident, no stoplight, no change in speed limit or narrowing of the road. So why the is there so much traffic? When traffic comes to a near standstill for no apparent reason, it's called a phantom traffic jam. A phantom traffic jam is an emergent phenomenon whose behavior takes on a life of its own, greater than the sum of its parts. But in spite of this, we can actually model these jams, even understand the principles that shape them, and we're closer than you might think to preventing this kind of traffic in the future. For a phantom traffic jam to form, there must be a lot of cars on the road. That doesn't mean there are necessarily too many cars to pass through a stretch of roadway smoothly, at least not if every driver maintains the same consistent speed and spacing from other drivers. In this dense but flowing traffic, it only takes a minor disturbance to set off the chain of events that causes a traffic jam. Say one driver brakes slightly. Each successive driver then brakes a little more strongly, creating a wave of brake lights that propagates backward through the cars on the road. These stop-and-go waves can travel along a highway for miles. With a low density of cars on the road, traffic flows smoothly because small disturbances like individual cars changing lanes or slowing down at a curve are absorbed by other drivers' adjustments. But once the number of cars on the road exceeds a critical density, generally when cars are spaced less than 35 meters apart, the system's behavior changes dramatically. It begins to display dynamic instability, meaning small disturbances are amplified. Dynamic instability isn't unique to phantom traffic jams. It's also responsible for raindrops, sand dunes, cloud patterns, and more. The instability is a positive feedback loop. Above the critical density, any additional vehicle reduces the number of cars per second passing through a given point on the road. This, in turn, means it takes longer for a local pileup to move out of a section of the road, increasing vehicle density even more, which eventually adds up to stop-and-go traffic. Drivers tend not to realize they need to brake far in advance of a traffic jam, which means they end up having to brake harder to avoid a collision. This strengthens the wave of braking from vehicle to vehicle. What's more, drivers tend to accelerate too rapidly out of a slowdown, meaning they try to drive faster than the average flow of traffic downstream of them. Then they have to brake again, eventually producing another feedback loop that causes more stop-and-go traffic. In both cases, drivers make traffic worse simply because they don't have a good sense of the conditions ahead of them. Self-driving cars equipped with data on traffic conditions ahead from connected vehicles or roadway sensors might be able to counteract phantom traffic in real time. These vehicles would maintain a uniform speed, safety permitting, that matches the average speed of the overall flow, preventing traffic waves from forming. In situations where there's already a traffic wave, the automated vehicle would be able to anticipate it, braking sooner and more gradually than a human driver, and reducing the strength of the wave. And it wouldn't take that many self-driving cars. In a recent experiment, one autonomous vehicle for every 20 human drivers was enough to dampen and prevent traffic waves. Traffic jams are not only a daily annoyance, they're a major cause of fatalities, wasted resources, and planet-threatening pollution. but new technology may help reduce these patterns, rendering our roads safer, our daily commutes more efficient, and our air cleaner. And the next time you're stuck in traffic, it may help to remember that other drivers aren't necessarily driving spitefully, but are simply unaware of road conditions ahead, and drive accordingly. In a hurry but love physics? We've got a book rec for you.
Okay, so you see the traffic jam, because one car brakes, the other at the back behind it has to brake, the other at the back also has to brake. So this erratic actually causing a ripple effect. So this ripple effect is actually giving us the chaos. So during the traffic jam is actually chaos. So that is what I encounter every day of my life when I want to go to the work, especially. And actually also during a holiday session. Nowadays during holiday everyone's coming out. In Malaysia we are lazy to cook, so everyone going out for eating. So during holiday the worst traffic jam would be occurred in Malaysia. So that is just for your knowledge. If you are coming to Malaysia, don't be surprised with the traffic jam. Even that is, I'm talking about highway now. I didn't talking about the federal roads or any road. It's a highway. So and that highway is actually we are paying for the toll. Each about maybe 10 kilometers or 20 kilometers, there is a toll I have to pay, but then it's a jam. So it's just because of this time and these things, and the more cars coming, right? So this is what chaos. Okay, so let's go to the application. So this is example of the application of chaos theory. So we have weather forecasting. In weather forecasting, even we can predict in a short period. We cannot predict in a long time. So because of this unpredictable, okay, and even if there is any tiny error, we input it in the system, it will be very vastly different in the outcomes. Okay, so the weather forecasting, even a best weather forecasting also, we cannot have a long period of forecast. And in engineering and physics, actually chaos describe the turbulent flow in the fluid mechanics, and engineers use chaos theory in variation control to ensure stability and reliability in mechanical structure. I will explain in deeper towards the end of my lecture about this. And also we have biology and ecology. We model the population, dynamics and ecosystem. Like for example, we have the system is about food supply, how many species are there. So it's all actually in chaos, because if you put it, I mean, if the species is more, I mean, we have the stable equation, we have the stable population in a time, but then when the species double, so the food chain, the food supply will be limited. So that in that particular time, the process will be very chaos, because you have so many species, so many population, but then your food supply is limited. Okay, so it's also, we can model through chaos. And last but not least, this is just an example of mine. We have cryptography and security. So yes, cryptography is also one of the application that we can use because of this randomness of chaos, whereby we can use the solution of chaos to use in cryptography as a key, and in fact to do the encryption algorithm. So So because of the randomness of the solution of the chaos, so it's very difficult. It's very difficult to for cryptanalysis to what we call to predict our algorithm, because I need to write this, right? I forgot. But then you can hear me, right? How about the recording? Okay, so yes, I'm using cryptography a lot towards my research for in chaos theory. So yeah, it's good. It's good because we have the system, we have the equation, and based on the equation, we can use the result to use for the key to design our algorithm, and we can see the system whereby the prediction our cryptanalysis is very difficult to go. Okay, so now I would like to talk about non-linear system. So we need to have this root because non-linear will give a result of chaos. Okay, so non-linear is referred to a system which the change of the output is not directly proportional to the change of the input. Okay, so unlike the linear system, small changes in the input is proportionally changes in the output. So I'm giving you the example here. As just now I mentioned y equal to 2x. So basically, if you go to the engineering, we have the Ohm's law, V equal to I R. So if you double the current, so the voltage across the resistor is also double. So that is very what we call simple and linear. So chaos is not that way. So it is involving non-linear, whereby, as I mentioned, the linear can be powers, can be product of variables, trigo, or exponential function. Okay, so that would be whenever you want to design a system, this non-linear term should be there. Okay, and the small changes in the output can lead to this proportionally large effect in the output, making the prediction will be much harder. Okay, so one of the example of chaos theory is logistic maps. So logistic map is actually we model the population dynamic. Okay, so small changes in the growth rate can lead to completely different behavior in population growth, ranging from stable to chaotic patterns. So basically, in chaos, we observe the stability. So we need to check the behavior where it start from the stable and it move to chaos. Okay, so this nonlinear give the sensitivity and the amplification, which is we call it as sensitivity dependence on initial condition. Okay, so now we take a look of the example. Okay, logistic map. So logistic map is governed by this equation, whereby the successive solution is according to the previous solution, and R is defined by growth parameter, and X is population, where we normalize from the range 0 to 1. Okay, at a certain behavior, at a certain value of R, this system will show a simple behavior whereby the point will be in the stable, we say converge. But then as we increase R, the system will be very chaos, where it demonstrates a period doubling oscillation, and at some points, the system will generate complex and unpredictable outcome, whereby we call it as chaos. So after this, we go in deep for this logistic map. Okay, so as I mentioned, double pendulum. So it's actually mechanical system. It's attached. One pendulum is attached to the end of the other one, and it consists of two rotating arms with its own mass and length. So in double pendulum, they involve a trigo. So this trigo will make the system non-linear. And if you have a small changes in angle or velocities, will be lead drastically different motion paths over time as the energy is transferred between the two arms. The system has a bit chaotic motion. Okay, so usually we often use double pendulum to study the chaotic behavior in the physics. So it's about energy. So usually when we talk about energy, we use a double pendulum. Okay, even minor differences in starting point will be result in significantly different output. Okay. Now we move to the non-linearity, where this non-linearity will lead to chaos. So there are three things, aspect that we have to check: the feedback loop and the amplification, bifurcation, whereby it's the transition of the chaos, and also the unpredictable in non-linear system, whereby we check the sensitivity analysis. Okay, so as I mentioned just now, nonlinear will produce feedback loop where the output affect the input. So it will lead the cycle we call isolation that can amplify the effect. Okay, so for example, as I mentioned, logistic map, the population generation affect the next generation. So if the population is too high, it will be reduced resources. So it will be lowering the next generation size. Okay, so this feedback will be create the oscillation, and at some growth rate it will be chaos. Okay. Also, we need to check the bifurcation, whereby bifurcation is very important. We need to check the transition of the chaos. So for the bifurcation, we need to check the parameter that what we call that will be affected or effect that will be affect the system. So it may be undergoes bifurcation, where point the system changes drastically. So bifurcation is actually the changes of the behavior and towards the chaos, the behavior will change drastically. Okay, so if you have double period bifurcation, we call it the behavior is moving from stable to oscillation, or maybe double oscillation. But then, if parameter continue to change, this doubling process happen repeatedly, so the system will become more complex, and this is whereby chaos come in. The system will not be predicted anymore. And unpredictability in nonlinear system. So this is where initial condition are very important, and this system governed by the set of rule will be they can be unpredictable because of this sensitivity of initial condition. Okay, so small changes or uncertainties in initial can amplify rapidly. Then we can the long-term prediction is impossible. Okay, and how the way we measure unpredictability or sensitivity depends on initial condition using Lyapunov exponent. sorry, my mistake. This is Y, Lyapunov exponent. Okay, so in Lyapunov exponent, we can see whether the system is in chaos or not. So in this slide, there are two major things in chaos theory, whereby bifurcation and also Lyapunov exponent. Okay, so Lyapunov exponent give us the knowledge of the sensitivity of initial condition. So this is a key aspect on how we need to understand non-linearity, whereby it leads to chaos. Okay, so I would talk about the butterfly effect. So this butterfly effect is actually metaphor from Lorentz. So Edward Lorentz is one of the mathematician that we can say that he is the one who discovered chaos. So actually what is happening during his time, he's actually want to predict weather. He's doing the weather prediction model. So he modified and simplified one model. He simplified one model. This is happened in 1963. Okay, so in that model, I would say he has this model and it's already simplified. I will give you the model after this, whereby in first he want to run it because he doing the weather prediction. So he run it, the weather prediction. He's using the initial condition of 0.506127. So this is the full precise value for the prediction that time, 0.506127. So there are 6 significant figures. Okay, so after he ran that simulation, he got the output of 2 months of prediction. Okay, and then all of a sudden he want to try another value of initial condition. So he just put, rather than 6 decimal places, so he just put 0.506. So he just take the first 3 decimal places, and then he go for a cup of coffee. After 1 hour, he come back and he got the result, the prediction, also for 2 months. And when he look at the result and he compared the result, he thought his laptop has a problem because the result is not the same. So, but then when he checked one line by line of the prediction, so at first the prediction almost the same, and then towards the next 1 decimal letters, 1 decimal missing and another decimal missing, and then the decimal missing, and towards the end, totally different output coming from the second one. So during that time, he realized that because of, I would say, when you go for the YouTube, you will say the word culprit is there. I mean, it's not a culprit, but then the initial condition, the second initial condition is actually the reason why the different result is coming. So that's why I mentioned even insignificant figures actually are giving us very vastly different output in this when we are talking about chaos system. Okay, so this is what I mentioned. So even tiny changes in the starting values of his weather simulate in and lead to vastly different outcomes, where this is showing the complex system could be highly sensitive to initial condition. Okay, and this sensitivity made the long-term prediction difficult. Even actually our system is a deterministic equation. So his findings fundamentally challenge that the belief of deterministic system, like weather, could be accurately predicted given the precise initial data. Okay, so this is actually just a metaphor, the butterfly effect. It didn't measure anything. So when you are talking about butterfly effect, it's just a metaphor. Okay, so the correct term should be sensitivity dependence of initial condition. So during his lecture, if I'm not mistaken, in 1963, he used this metaphor whereby the butterfly flapping in the wings in Brazil actually can cause a tornado in Texas. So it's a two different continent, but then because of the butterfly flapping in Brazil, the tornado will cause in Texas. So this is the metaphor that he used. Okay. So actually, why bother with butterfly effect? So we just want to mention that butterfly effect is actually captures the essence of chaos. So and then butterfly effect will limit the predictability, and even we know the governing rules perfectly, but we cannot completely control the outcome because of this sensitivity. Okay, so this system feature will diverge with a very tiny difference. So that is what we call a butterfly effect. Okay, so in real world example, we already discussed actually all these things. It's actually the butterfly effect gives an intuitive gateway into chaos theory to set up for the mathematical rigor in the next section. Okay, so after this we go to the mathematical rigor for this butterfly effects, which is we call it as sensitivity dependence on the initial condition. So we just want to see how tiny difference of initial condition would lead to very vast different outcomes. Okay, for example, if you have a tiny variation in the air pressure, so initially the significance the initially significant we can alter the wind pattern, whereby it will be shift weather condition thousands of miles away. Okay, and in financial market, as our friends just now giving the example, a slight change in the interest rate will cascade or affecting investor confidence or stock market worldwide. So prediction of the financial stock market is quite difficult. I mean in the long run. And also for biological system, I'm giving example here, a tiny increase in temperature. So it's just a temperature difference, but then it will be slightly alter the insect production rate, okay, reproduction rate, okay, because the temperature, sometimes the higher temperature will lead the increases of reproduction rate, so leading to for more food for the certain bird, okay. So which is they impact the predator higher up for the food chain. So everything has the consequences. So that's why in many biological system that we can use to model, so we can see we can see how the behavior of the system happen. Okay, so now this is the mathematical rigor of the chaos theory, sensitivity dependence on initial condition. So what does it mean? It means a tiny difference in the starting condition would lead to exponentially diverging outcomes. So these properties actually will make the system, the chaotic system, unpredictable. So we use Lyapunov exponent to calculate or to measure, and how we relate to chaos theory, because sensitivity dependence is actually a central of chaos theory, because it introduces unpredictability in deterministic system where it governed by a fixed rule. So even we know the exact governing equation, because of this exponential divergence, we cannot predict the system. Okay, so I want to talk about the Lyapunov exponent because it measured the sensitivity dependence of the initial condition. So Lyapunov exponent, they measure how fast the trajectories path diverge or converge from each other. So you need to imagine you have two tiny difference of initial condition. So we want to see how it diverge or how it converge. Okay, so it quantifies the rate at which two points that start very close to each other. So we want to see whether it come closer or move further from the system as the time evolve. Okay, so basically we use this equation to calculate, to measure the Lyapunov exponent, and the result would be either the Lyapunov exponent is positive or negative or 0. There will be three possibilities. If the Lyapunov exponent is positive, we would say the trajectories or the behavior of the system is diverge, and hence we can say that the system is chaos. Okay, whereby if the Lyapunov exponent is negative, the system trajectories is converged to one point, and we would say the system is stable or dissipative. And what about we have 0? If the Lyapunov exponent 0 is actually, we can say the constant distance is maintained. I mean, it will be the same because 0. Because when we talk about Lyapunov exponent, we check the difference between 2 points. Okay, so if there is 0, there is no distance at all. So the system behavior would say the quasi-period or marginally stable. So that is what we will have for the Lyapunov exponent. Later on also we will go for the MATLAB, how to find the Lyapunov exponent. Okay, so how long I have actually? What time your lunch hour break? Oh, it's almost 2 minutes more. Okay, so we check this time series. This is time series whereby I have 3 initial condition here. As you can see, it's very insignificant difference from each other. But then, as you can see, towards the time evolve is basically about the same. Towards the end, it's diverging. I mean, the trajectories is not the same at all after the time evolve. So this is what we call sensitivity of dependence of the initial condition. So we will do this later, so you can see. You will see actually the time series fluctuate in the not the same manner. Okay, and also this is the graphical representation of phase. Okay. So I'm giving you the same, I mean slightly difference of initial condition from here, but then as you can see the trajectory between these 2 points will be very different. Okay, so but then it's still confined like the same pictures, right? Why that is happening? Even the result is different, but then it's still confined the same pictures. I mean, in the same butterfly. I say this one is butterfly because this is what Lawrence found. So it's still even you can see the difference, but then the pattern would be like butterfly. So this is why, because chaos also we would say bounded. Okay, so boundedness is also important. The trajectories will not going far, it will be bounded in the same manner. Okay, so Okay, so this is practical application of sensitivity dependence. I'm giving you in two. One is in the engineering and one is for the prediction. So this is the challenge actually for the engineers and for prediction to do and to have to do something. So for example, in aircraft stability, okay, we have a few parameter, I would say few state variables that is important, like airflow, weight, and control input. So you need to make sure the flight is stable. So if there is a turbulence happen, so means when you have the turbulence means chaotic is there. So how you want to manage the aeroplane? So that is why chaotic very important for engineers to check the system when the system is chaos, so they can have the control input to their system. Okay, so for example, we have the autopilot system in aircraft. We have autopilot system. So this autopilot system will make continuous adjustment to keep the aircraft level and on course. So this autopilot actually developed after we check the chaos behavior. Okay, so this is very important. So financial also we have, I'm giving here the parameters or the variables that is very important, whereby it leads to the chaos. So with different error, our initial condition will lead to different forecasting. So so this is what example that I can give to show why chaos theory is important and why this is challenge for the engineers and also for the prediction to do. Okay, and lastly, I would like to emphasize the difference between butterfly effect and sensitivity on initial condition. So butterfly effect is actually just a metaphor, and sensitivity on initial condition is actually the what we call the mathematical properties of chaos, whereby we measured by Lyapunov exponent. Okay, I want to show this one, but I have no time. I don't know. Well, I'm not enough. Okay, so logistic map. This is actually one of the example. We will say road to chaos. Okay, I will make it in fast because we have time. Okay, so when you have this one example of R equal to 2, so we have the stable equilibrium, which means the point stable to one point. Okay, and then when it moves to R equal to 3.1, we have the simple oscillation. As you can see, the system doubling. Okay, oscillation. Towards to 3.5 or 3.55, the complex oscillation occurred. So in this one, it's still not chaos, but then the doubling of oscillation to 4 to 8 to 16 to 32 and so on. And when you change your R to 3.57, the system fully chaotic. So in this state, the population values no longer settle into a repeating cycle. So there will be no repeating, there will be no oscillation after the chaos behavior. Okay, so this is the example. I don't know if you can see this one. I think it's very nice. It's very nice. So from the start 0.1, it's converged to 1 point, and then it moved to when A is R to 2, A equal to 3, A equal to 2.1. How many stable points there are moving, and this is the oscillation happening to 3.1. So maybe 8 here, the oscillation is 3.2, maybe 16. The oscillation happened 3.5, maybe 16. You see the moving, and 3.55, maybe 16 oscillation happening there. And now if you move towards to 3.7, it will be root to chaos. So that is the hallmark of chaos. Okay? And this is Hanon map. So in Hanon map, maybe it will be the same. I mean, if you have, okay, this is the equation of the Hanon map. So I am doing it fast. So A is giving the system, is affect the system. So if you can see here, I'm changing the value of A from A equal to 1, A equal to 1.2. You can see the behavior of the system is different for each value of parameter. So towards when A equal to 1, we have the stable behavior. When we have A equal to 3, we can say bifurcation almost happening. I mean, chaos is almost happening. And when we have A equal to 1.4, the chaotic behavior is there. So, and this is what we call the strange attractor, whereby it is bounded, non-periodic, and it is very sensitive to initial condition. Okay, this is what I mentioned. I want to show you Lorentz system. So this is Lorentz. So this is the equation of Lorentz. We will go deeper to after this. So in this system, X is represent the convection current, Y is represent the temperature variation, and Z is represent the vertical. So Y is horizontal, Z is vertical temperature. Okay, and sigma, rho, and beta is also represent something. And there are two nonlinear terms here, whereby you have X, Z. It's just a product, right? It's just a product of variables X, Z, and XY. There are only two nonlinear, but then this nonlinear makes the equation something happen. I mean something else. Okay. And I'm showing you here also the different type of behavior when we change the row. Okay. At row 5, you have stable, converge to a fixed point. And then we have row 15, whereby the oscillation begin. It started to begin, predict behavior. And when we have row 28, we have the chaotic behavior. So actually, I thought I have time, so I want to go deep for each, but then I just touching. So hopefully you can try to understand. And we will go for later. Okay, so this is the application. Also, I have been talk about it in just a few slides just now. So this one, we managing chaos in variation control and chaos cryptography. So we are using the sequence of the solution for the key and also for to design an algorithm. And also predictive modeling. I also touched the prediction, whereby we cannot predict in the long run. We can have in the short term only. And for sure, we have to use the competition technique for this type of equation. And to expand chaos theory, so we have machine learning and AI, quantum chaos, and chaos in neuroscience. So basically, in this key 1 and key 2 is my future direction. So I will go for this, and there are few questions to raise how we want to highlight chaos in this field, ML, AI, and also quantum. Because nowadays, I would say maybe 10 years after this, we will have the quantum crypto, whereby our current crypto cannot survive already, because in a second, our secure data will be just being exposed by this quantum. So that will be my future direction. Okay, so as a conclusion, so we already explored the foundation concept, the deterministic, the non-linearity, and the butterfly effect. And we already see the changes on the initial condition will lead to very drastic different outcome. And I'm giving you a few examples just now. It's actually a very simple one, but then it produces a complex and unpredictable behavior, but with a governed governed by a set of rules. And also I'm touching about the real world application in variation control, chaos theory, and also predictive learning. So it's quite faster because we don't have a time, but then we go deep for the next session for chaos, especially for Lorentz and Rosler. So after this we go deeper into the dynamical of chaos, Lorentz and Rosler. Okay, so with that, thank you. I'm giving my phone number and also email. You can email me if you have any question, or you can text me if you have any inquiries to ask. Okay, so with that, thank you. We meet again after this. Sorry, taking you 13 minutes.